Hello everyone, welcome to this machine learning teach by doing lecture. In this lecture, we are going to be looking at a hands-on implementation of neural networks in Python. We'll be taking a problem and then we will construct the neural network architecture. We will train the neural network and then we will obtain results. And then I'll also show you testing. We'll be using some standard libraries in Python which are routinely used by engineers in practice. If you want to see a much more detailed version of how to create a neural network from scratch, I have started another series called Neural Networks from Scratch, and that has 3 to 4 videos so far, in which we'll be breaking down the commands which these libraries such as TensorFlow and Keras use. But in this lecture, I'm going to use the commands straight from these libraries because the main aim of this lecture is to show you how neural networks are used in practice today. If you want to get a much more theoretical understanding, please take a look at the neural network from scratch series, and I'm attaching the link to it in this video for your reference. So let's get started with today's lecture. Before we move to the problem and before we actually start coding in Python, I want to first describe about 3 frameworks which typically you must have heard about or you will hear about when you think of coding neural networks in Python. And those 3 frameworks are as follows. The first is something called TensorFlow, the second is something called Keras, and the third is something called PyTorch. Now, most of the students either use one of these, or many students actually don't know the difference between these three. So, let me explain to you each of them. First is TensorFlow. And if you go to the TensorFlow's website, you will see that TensorFlow is basically a platform for running machine learning models or machine learning frameworks. It's developed by Google, and many Python codes which are used today use TensorFlow. That's number one. The second thing or the second term which you will hear about a lot is something called Keras. Now, Keras is a bit different than TensorFlow because Keras is like an API. So basically, you can think of it as basically functions which you can invoke. So, for example, if you want to chain different layers together to create a neural network architecture, you can use the sequential API call from Keras. Similarly, Keras just makes it easier to write down functions. If you want to implement a dropout layer, instead of coding the dropout layer from scratch, you just have one command for it. Instead of specifying the loss function and instead of explicitly writing down the gradient descent rules, you can do it very simply using the Keras interface, which is also called as an API. So Keras is a neural network API and TensorFlow is a platform for ML. So what people did was that they integrated Keras with TensorFlow. So TensorFlow and Keras are now integrated with each other. Um, and the code which we are going to use today will actually use Keras within TensorFlow. So you can think of as TensorFlow as the bigger machine learning library, Keras as the neural network API. So basically making it easier to call neural network functions. And then Keras was merged with TensorFlow so that we can call the Keras functions by using TensorFlow itself. Then there is one more library which is called as PyTorch. Now, PyTorch is also a machine learning framework, and you can define and run neural networks using Python using PyTorch also. It was developed by Meta, which was earlier called Facebook. Now, there is a big difference between PyTorch and TensorFlow, and I will try to simplify that difference for you as much as possible. So, first, let's look at simple codes in TensorFlow and PyTorch, which you will write to create a neural network. So, for example, here we are using TensorFlow. You import TensorFlow as TF, and then remember I told you Keras is integrated with TensorFlow. So, if you want to use the layers API within Keras, all you need to do is from tensorflow.keras import layers, and then you can define the layers of the neural network. You can even import sequential. So here we have defined a neural network which has 10 input features and one output. On the other hand, if we wanted to do the same thing with PyTorch, the implementation kind of looks like this. So PyTorch follows a more object-oriented approach where we define a class, then we define two methods within the class. So underscore underscore init underscore underscore is a special method which is called automatically when an instance of this class is created. Then we define the weights of this neural network, 10 input features, one output. The second method is forward. So this implements a forward pass and then returns the output from the neural network. So there are two different ways of writing the same neural network. TensorFlow uses more like an API based approach or chaining functions together, and PyTorch uses an object oriented programming approach. But there is a subtler and a bigger difference between these two. TensorFlow uses something which is called as a static computation graph, and PyTorch uses something which is called as a dynamic computational graph. So let me try to actually explain to you what these mean. Okay, so let's say we want to compute the summation of two functions. So remember TensorFlow uses static computation graph. So we define the compute function and then we say that c equal to a plus b. Now, if you want to modify something in this function, you need to write a different function. So compute extended c equal to a plus b, and then let's say I want to define another variable called d, which is c multiplied by 2. So that is another variable. So you cannot just extend this function very easily. You have to write another function. The reason is because once this function is defined, a static computation graph is created by TensorFlow, and it becomes very hard to be flexible with this function now. That is the simplest way to describe it. Whereas if you use PyTorch, you can change things on the fly. So initial addition can be performed dynamically where c equal to a plus b. Then you can also add another operation dynamically, d equal to c into 2. You don't have to define a separate function for it. Essentially, what I'm trying to say is that PyTorch is a bit flexible with the code because it creates computational graph between variables on the fly or on the go as the code is being run. Whereas TensorFlow creates the graph in a static manner. So if you want to change something, then we need to redefine the function itself, and so it's a bit less flexible. In summary, both TensorFlow and PyTorch can be used by beginners, but remember that TensorFlow is fast, robust, but it's not very flexible. So if you want to toy around with stuff, if you want to use this for research, TensorFlow is not very recommended, but it's actually quite good for production level or industry level machine learning frameworks. PyTorch, on the other hand, generates these graphs in a dynamic manner, so it's very flexible. So if you want to change stuff on your own, be use these frameworks to do research, then PyTorch is very good. As a beginner, you can use both PyTorch and TensorFlow, and in fact, I encourage you to use both to see the similarities and the differences between the two. In this particular video, we are going to be using TensorFlow. So I hope you have understood the differences between these three frameworks now: TensorFlow, Keras, and PyTorch. Basically, you can think of TensorFlow and Keras in one bucket and PyTorch in another bucket. So let's get started with today's example. Today, what we are going to do is we are going to perform a simple classification task. First, let me introduce you to the input data. Our input data or training data looks something like this. Every input has two attributes, x1 and x2. So if you plot them, it will look like this. And every input also has a color coding associated with it. So essentially, there are three color codes: R, G, or B. So any point x1 comma x2 which you take, let's say we take this point, this is coded as red. If we take this point, it's coded as blue. If we take this point, it's coded as green. This is also called as the spiral data. Our goal in this lecture will be to design a neural network which which takes in an input and can make a prediction regarding whether it belongs to the R category, G category, or B category based on the training data. I hope I have made the problem clear. If any new input is given to you, let's say which lies somewhere here, or even if the input is in the test data and not in the training data, the neural network should take the input and classify which of the three color categories the input belongs to. So this is clearly a classification problem. So to start thinking about this problem itself, first you need to think of the neural network architecture, and this is a bit flexible. So you can start out with anything which you want. The architecture which I am going to start out with is this: I am going to have 64 units in the first layer, and I'm going to have 32 units in the second layer. So I'm going to have an input layer in which x1 and x2 come in. Then I'm going to have first hidden layer, second hidden layer, and then the output layer. Remember, output layer should have three neurons because we want R, G, and B. Okay. So the first hidden layer has 64 units. So let me mark these with a tick. First hidden layer has 64 units. Second hidden layer has 32 units. Okay. Another choice which you need to make apart from this is what are the activation functions which you need to use. So the first choice which we made is number of hidden layers. Second choice which we made is number of neurons. Third choice is the activation layer in each layer, or the activation function in each layer. So we need an activation function for the first hidden layer, one activation function for the second hidden layer, and we need one activation function for the output layer. So we have already covered a lecture on activation functions. So remember that for classification tasks, the output layer has to have a softmax activation. So this is fixed because there are not too many options. So if the input belongs to the red class, the first neuron will have the highest probability. Second and third will have low probabilities, or they will not fire. We only want the first neuron to fire if the input is red. So the output neuron should essentially represent probabilities, and that's why we will be using the softmax activation in the output layer. Now, what is to be used in the hidden layers is generally flexible, and you can use many activation functions such as ReLU, Sigmoid, TANH, etc. I'm going to be using ReLU because it's the safe initial choice to go with. So if you're a beginner, I would suggest to use ReLU in the hidden layers. And if it's a classification task, you can use softmax in the final layer. If it's a regression task, you can always use ReLU in the final layer. Okay, so this is the architecture which we are going to use, and I have just represented it over here. The second choice which we need to make is regarding the optimizer and regarding the loss. So once we fix the output activation, the loss also kind of gets fixed because we are using the softmax activation. So the loss which comes with the softmax is the categorical cross entropy loss. Just to revise your memory, the categorical cross entropy loss looks something like this: negative sigma true label into log of predicted. So another simple way to think about this is just negative log of the correct class prediction. So if the input correct class is red, we look at the three outputs, and we, if let's say the outputs are zero point 0.7, zero point 0.2, and zero point 0.1, and the input is R, its true value is R, which means red category. So the other two neurons don't matter to us because they don't belong to the correct class. So these two don't matter. So the loss will be negative log of zero point 0.7, which will be around, I think, 0.35. So as this output gets closer and closer to 1, the loss starts decreasing. And when this output becomes equal to 1 of the first neuron, then the loss becomes 0, because then that's exactly what we needed, right? Since it belongs to the red category. So this is the categorical cross entropy loss which we'll be using. And for the optimizer, we'll be using the Adam optimizer, which is generally the most commonly used optimizer in neural network tasks like these. I'll also show you stochastic gradient descent and stochastic gradient descent with momentum. We have had lectures for these in the past. So you will directly relate to what we learned in the theoretical lectures. So I hope you have understood the architecture which we are going to go ahead with and the optimizer choices which we are going to go ahead with. Remember that in the future, if you want to solve any problem using neural networks, before jumping into code, it's always better to make a rough sketch. Think of the units, the activation, the output activation, then the loss function, and the optimizers. Once you have thought this through, then it's a good idea to move towards the code. So now I'm going to be taking you to the coding interface in VS Code. So first thing which I'm going to do here is zoom in a bit. So let me go to appearance and zoom in, and let me actually zoom in one more time just so that we all can see the screen clearly. So appearance, zoom in one more time. Great. So I think this should be enough. Okay. So this is the code and I've named it spiral underscroll nn.ipynb. I'll be sharing this code with you, so don't worry. Okay, so the initial task is to load the packages. So I'm going to comment here loading the packages, and we are going to load the following package. We are going to load NumPy because it will help creating arrays for scientific computing. It's always preferred. I'll use matplotlib essentially for plotting. Then I'm going to be using sklearn, which is scikit-learn, because I want to use the train test split to split the data into training and testing. Then I will use again scikit-learn and import standard scalar. This helps to take subtract the mean and normalize the data, which we'll be doing for both the training and testing data. And finally, as I mentioned to you before, we'll be using Keras. So we'll be using two functions from Keras, sequential and dense. Sequential is to chain the different layers together, and dense is essentially to create a fully connected dense neural network. So let's get started. The first task which we'll be doing is to generate the data itself. So I'm not going to be focusing on how I have generated the data here, because you can generally, for all neural network related problems, the data is already available. For the sake of demonstration, I have just written some function using sine and cosine to be so that we can generate the spiral data. So I'm going to run this part of the code now, where we'll be also plotting the spiral data. I'm taking a total of 999 points. 333 will belong to the red class, 333 will belong to the green class, and 333 will belong to the blue class. So let me run this. Okay, so I have run this piece of code now, and you can see that this is how the spiral data actually looks like. I had already shown this to you in the whiteboard, but here you can see we have generated this in VS Code. The input has two attributes x1 and x2, and each data point has a color. Either it's red, it's green, or either it's red, it's green, or it's blue. Great. So the data has been generated now. Uh, After the data has been generated, it is very important to have training data and testing data, because ultimately what is important to us is how well we are doing on the testing data. So we are going to use this command called train test split, which is obtained from scikit-learn.model selection. What this command does is that once we give the x data and the y data, it will automatically divide it into training and testing based on the test size. So here I am giving a test size of zero point 0.2, which means we'll use 20% for testing and we'll use 80% for training. Let me just quickly plot the x and y values for you to see. If you plot the x values, they will look something like this. These are x1 comma x2 pairs. And if you plot the y value, they will look something like this: zeros or ones or two. So that's R, G, or B. I'm going to delete this cell now. So these are the x So now this is the train test split. X train and X test will be the X1, X2 values for the training and testing, and Y train and Y test will be Y1, Y2 values uh, for training and testing, or rather not Y1, Y2 values, 0, 1 or 2 for training and the testing data. And remember, this random state helps us to initialize the same way every single time. So this is the command which you need to do to split the data into training and testing. When I share this code with you, I encourage you to try different test sizes and see the output and how it changes. Ideally, if the test size is too large, the error will be very high. But if the test size is very, very small, we are likely to be overfitting. So that's also not good. Usually, I start with point 0.2. Then we are going to use the standard scalar function, and we are going to apply this to the X train, and we are also going to apply to the uh, X test. The reason is that we want to basically standardize the data. Essentially, what we want is that, let's say, if you have data, and let's say one data x1, let's say, is very high, and x2, or let's say one input value is very high and second input value is very low. What this actually does is that it confuses the neural network and the training time increases that much. So what we do is that it's a common practice to take the input values. So let's say this is the x1, x2 input values, right? X1, x2, 1, and we have 999 values like this. So what is done is that from this matrix we first subtract the mean, so mean of x, and then we divide the standard deviation of x. So what this will do is that every single row will kind of have similar minimum and maximum values. So it will never happen that one feature value is incredibly large while other feature value is incredibly small. This will never happen. We will make sure that everything is standardized, and that's the reason why this scalar dot transform is used for the training data and for the testing data. It's not needed every single time, but I have seen that using the scalar dot transform, it accelerates the training process, because then features are of the similar magnitude and similar scale. Okay, so up till now we have the training data, we have the testing data. So let us actually visualize the X trend scaled and let us see what it looks like. So if I just, let me scroll up a bit. So here I am visualizing X trend scale. So look at these values versus if you just look at X train uh, and X train scaled, you can see that the values are first of all different, they are not the same. And this is because we have used this subtraction of the mean and divided by the standard deviation. So here you can see that all values kind of lie between -1 and 1. There are some values which go up to -2, let's say, but almost all the values will have similar input, similar minimum and maximum values. Next, what we'll do is that we will actually define the neural network architecture, exactly like what we had seen over here. So remember what we saw here. We are going to use two hidden layers. The first layer has 64 units and the second layer has 32 units. And Relu, and the final one has softmax. Okay. So let us define the model. First, I do this sequential, and this is from Keras. This tells Keras that we are defining the neural network and we want to chain different things together. So first we create a dense layer. The reason we use dense is because it's a fully connected layer. And the first layer has 64 units and it has two inputs. And the activation is ReLU. So look at the first layer. The first layer has 64 units. It has two inputs and the activation is ReLU. This is exactly what has been defined over here. Then what we actually do is we add another layer whose which is fully connected, which has 32 inputs and whose activation is ReLU. We don't need to define the input dimension here because it's automatically understood that the output of this first layer is feeding into this. So we don't need to specifically write the input dimension again. And then we write the final layer. So remember, the final layer essentially has three neurons and the softmax. So when we write the final layer, it will look something like it has three neurons and the activation is softmax. Great. So I'm just running this part of the code and right now it's done. And now we come to one of the last steps of the process, which is writing the optimizer. So the neural network architecture has been defined, weights have been initialized, but weights have not been optimized yet. And for that, we need to define the optimizer. As we saw here, we are going to be using the Adam optimizer, and later I'm going to show stochastic gradient descent and stochastic gradient descent with momentum. So first, let us say that optimizer is Adam and the loss is categorical cross entropy. So the loss which is to be used is the categorical cross entropy loss, and the metric is accuracy, which means we'll be looking at accuracy when we actually compare the model performance. So let me run this. So remember, this comes under model.compile. So up till now, from Keras, we have used model.add and model.compile. And the last thing which we will be using from Keras is model.fit. What this will actually do is that after we have defined the optimizer and after we have defined the loss, we'll be doing the training process, which means that the weights of the neural network will be adapted, and ultimately they will be adapted so that the loss between the data, training data, and our neural network prediction on the training data is as low as possible. And here I am also plotting the validation data, which means how well we are doing on the testing set. I am doing 50 epochs. So let me run this particular code. So I am running this right now. Here you can see the epochs are updating 1 out of 50, 2 out of 50, and you can see the accuracy at every step. So the accuracy started out with 0.41, which was not very good, but here you can see as we reached 50 epochs, the accuracy reached 0.9946, which is very good. Remember, epochs is going through the entire training data once, so we are doing this 50 times. And the validation loss, it's important to look at the validation loss also, because usually that is the metric which we actually care about, how well we are doing on data we have not seen. So validation loss was also pretty high initially, but as we go down, you can see that the validation loss went to 0.0225, which is very good. Now, how do we know whether the validation loss is enough or not, or should we keep on going further? One good way is to plot the training loss, to plot the validation loss, to plot the training accuracy, and to plot the validation accuracy. So let me plot this actually. So here I have plotted this for, and I want you to very keenly look at, first let's look at the training loss that's written by this blue arrow or this blue line. The reason we know 50 epochs are enough is that the training loss has started to decrease and then it has started to stagnate now. So probably it won't go even further. Then, but we will test this just in a moment. The validation loss is also decreasing, which is very good. The training accuracy, which is this green line, is increasing and it has stagnated. So you see for 30, 40, 50 epochs, the training accuracy has stagnated and the validation accuracy has also stagnated. This means that we probably don't need too many epochs more. But let us see what happens if we increase the epochs. So now I'm going to increase the epochs to 200. Just keep this final accuracy score in mind, 0.9946, and let us see how we are doing with 200 epochs. So I'm running this right now, and here you can see this will run for a bit longer period of time, because now we are running it for 200 epochs. So 50 epochs are completed and it's still running. Now around 90 epochs are completed, and now we are at around 120 epochs. So it's fast, so we don't need to wait for too much amount of time. But already if you see at the loss, it's not changing too much after this point. which was kind of what we expected. So now 200 epochs have been done. So let me plot this. So this is the plot with 200 epochs. You can see that after 50, everything has stagnated. Even the accuracy has stagnated. So we don't need these many epochs. It's fine to have 50 epochs as well. So this is how you actually judge how many epochs you need. You look at the plot of the training loss, training accuracy, and you look at the plot of the validation loss and the validation accuracy. If the plots actually start to stagnate, so I'll need to initialize once more to run this. So if the plots actually start to stagnate, it is a sign that we don't need more epochs. We can stop at that particular point. Okay, so here it's again showing the plots for 50 epochs, the loss plots and the validation plots. The loss plots and the accuracy plots have stagnated for the training and validation data. So which means the architecture chosen is pretty good and we have reached an amazing level of accuracy for the test data. This is how you train neural network models. Using Keras, it's very simple. You see, we just did three things. Using model.add, we created the architecture. Using model.compile, we specified the optimizer and we specified the loss. And using model.fit, we actually did the training. So all the lectures about back propagation, which we looked at in the previous lectures, those are actually covered in this fit command. So back propagation is happening underneath the surface or underneath the hood as it's called when we run this command. If you want to see how back propagation actually works in action, I encourage you again to follow the neural networks from scratch series. Okay, great. So we have the loss plots and we have the accuracy plots. But now let's do an important thing. Let's actually compare the true value with the predicted value. So in this particular piece of code, what I'm doing is that I'm actually just writing the predictions for the test data and I'm plotting the predictions. So here you can see in one figure, on the left hand side you can see the true classes, on the right hand side you can see the predicted classes. And you can see that our neural network is predicting perfectly. And remember, this is test data. So this was data not seen to the neural network. This is not the training data. Of course, it will do well on the training data because it has seen that data, but this is the validation data. And we already knew this would be good because look at the validation loss. The validation loss has become almost zero, and the validation accuracy is almost 90%, as we have seen. So that's why the true classes and the predicted classes for the test data look almost exactly alike. This is a great because our neural network is not overfitted. It learned very well on the test data. I want to do one more thing now. I want to show you if a new point is given, what is the classification of our neural network. So remember that once a neural network is trained, for any point given to it, it will predict whether it's R, G, or B. So if your question is that what if a point is somewhere not in the test data but somewhere else? It's fine. Our neural network is now trained, so it will predict for that point. So I'm going to show you those predictions. So I'm going to take a new point as point 0.1 and minus point 0.5. So it will lie somewhere over here. Point 0.1 and minus point 0.5. So it will lie somewhere over here. And I want to predict whether it belongs to the red, the green, or the blue. So it kind of lies closer to the blue, right? So I hope the neural network gives blue as the answer, but let's see. So again, I'm doing the prediction here. So I'm doing the prediction based on my final predict. So remember, if you want to do the prediction, you need to use the model.predict from Keras. So I'm doing the prediction and I'm encoding that if the prediction is 0, use the legend as red. If it's 1, show me green, and if it's 2, show me blue. So let me run this. So look at this particular. So this is that data. This is the new data point, which is shown in yellow. And look at the prediction. The neural network is predicting that the new point is blue. This is exactly what we had hoped, right? Because it's more closer to the blue data. Remember that this is not k nearest neighbor. So although our intuition says that this yellow is closer to blue, this data point is closer to blue, so it should be classified as blue. It does not work like that since it is not k nearest neighbors. But I was just telling you for visualization purposes. So within just 60 to 70 lines of code, I have demonstrated how you can run code and run a simple neural network for a spiral data like this, and how you can classify which class it belongs to, red, green or blue. Now think of all the types of problems you can solve. Using the same code, you can solve any kind of classification problem. For regression, it's exactly similar. You just have to change the activation function in the output to maybe a ReLU activation function. So you can use this code as a template to solve many problems with neural networks. One thing I wanted to show you is the loss when we use different optimizers. So now if we use a stochastic gradient descent optimizer, let's say, let us see the loss with it. Remember with Adam, the loss was going to almost zero and the accuracy was going to around 0.99. Let's see what the accuracy is with the stochastic gradient descent. So here I am using tf.keras.optimizers.sgd, which is stochastic gradient descent, and I'm going to run this. Okay, and I will run 50 epochs again. So let us try to have a look at the accuracy. So you can see that the accuracy is struggling a bit, right? The maximum accuracy which it reached is 0.7799. And if you plot this here also you see that the accuracy is not actually, look at the accuracy plots, it's not going to zero point 0.9. This is again an indication that Adam is a better optimizer than stochastic gradient descent for most neural network problems. Now let us try to use momentum. As we saw, momentum really helps accelerate gradient descent, and it is possible to give momentum as an argument here. So I'm now including momentum. So momentum, remember, uses a running average of historical data, and that way it actually helps in faster training, and it can lead to more efficient or accurate values. So let me run this now. First, let me reinitialize the neural networks. Let me run this model.compile, model.fit, and now let me observe the accuracy. So here you can see, as expected, the accuracy is now going to 0.99. So the accuracy is now 0.9925. Let me show this in plot. Amazing. So now look at the accuracy plots. They have reached around 0.99, which is exactly similar to what we had observed for Adam. This is the advantage of using momentum. In fact, if you have learnt about the Adam optimizer, it's just a mix of momentum and an optimizer called ADA delta. So we would kind of expect that momentum does better than stochastic gradient descent. So like this, once you get this code, you can play around with different things. You can play around with the train test split. You can play around with removing this normalization. You can play around with the optimizers, the units, the layers, and you can also play around with momentum values, different optimizers, and the number of epochs as well. So remember that for training a neural network like this, the real skill of an engineer comes from also knowing what is the architecture to use, what are the units to be used. So let me make a list of what all is important. So first, what is important is the architecture. What are the number of units to be used? What are the activation functions to be used? Second thing which is important is optimizer. So which optimizer do we need to use? Do we need to use the Adam? Do we need to use stochastic gradient descent? Do we need to use the momentum? If we are using the momentum, what should be the value for the momentum parameter? Third thing is, what is the loss function which we want to use? Fourth thing is, what is the train test split? Fifth thing is that, do we want to normalize the inputs? And there are some other considerations which I have not covered here. Should I add a dropout layer? Should I do something called like batch normalization? So right now we only normalize the input data, right? We are not normalizing the output which comes from each layer. So in batch normalization, that is also done, which sometimes improves efficiency. Dropout also prevents overfitting, and it leads to regularization, which improves the generalization or the test accuracy. In this example, we did not need to do these two things, dropout and normalization, batch normalization, but they are quite important. So, as a neural network or as a machine learning practitioner, remember that always keep these six things in mind. Do not just blindly execute codes, but always try to think from scratch what are the effects of each of these things and then change them accordingly. And I hope the previous lectures which I have had on neural networks will help you choose different things like architecture, optimizer, loss function, train test split, etc. So thank you so much, and I hope this lecture added value to your lives. I'll be sharing the code file in the information so that it will help you run this code and also run other codes. So again, thank you everyone, and I look forward to seeing you in the next lecture.